Continue on Chapter-8. So Chapter-8 we will study the electron configurations. Electron configuration. So that means you want to find out where are the electrons. Alright. So we studied from Chapter-7. We find out electrons. Electrons are in the so-called orbitals. You can take both those the scantron for the even number and odd number, or you can all take it back. You will use the even number for Chapter-8, but you can keep those for the odd number for Chapter-7, 1, and 5 to study for the second exam. Alright, so we know electron in the orbitals. So then to representing those orbitals, we have two ways. One way we study is the configurations, and the other one is diagram. So today we're going to study a little more about diagrams. I think the diagram, this concept you already learned in the Tuesday's class. Right. So those orbitals, we can represent those orbitals by those notations. So as you know, orbitals. 71. I think it's 71. Correct. Did you find the given number for the? Yeah. Do you have the? You still have the Chapter-6 one? You find those Chapter-6 here. You can keep those odd number because we already finished those 1, 3, 5, 7. You should be able to find the given numbers. Yours, you probably just sort and just write down some papers.
Okay.
Yeah, and then we'll probably give you a new scan card.
Okay.
Yeah. All right. So orbitals is the place the electron is in, and orbital we know those can be in the so-called subshells. Right, so orbital is a region of inner space, right? So you can have a different shape for the orbitals. So here is the organization. So orbital organized into subshells. So common subshells is S subshell, and P subshell, D subshell, F subshells. So therefore, to get the electron configuration, you just find out how many electrons in those S subshell, what S, and how many in the P subshell, and so on. So those we studied in the Tuesday's class. So then today we also studied this Tuesday too. We also studied the diagram. Diagram, which means you just draw a square or a box. So with diagram, we can find out little more details. Like when you write something, those electron in the S is similar as one orbital. If we have 6 electrons, or we have like different number of electrons in the P subshells, we might have 3. So now, where are the 3 electrons in those subshells? Because the subshell, like the P subshell, has 3 orbitals. So if you use the diagram, and you know like in details, you can also like show someone else in details where are the electrons. Alright, so again emphasize the orbital just draw like a rectangle or a square or a box, and that's just one orbital. And if you want to show like there's 1 electron in it, you just draw 1 arrow. And if you want to show that there's 2 electrons in it, you draw 2 arrows. Make sure if you draw 2 arrows, the 2 arrows direction should be opposite. Right. So now let's see this example. We want to write the orbital diagram for sulfur, and so then we can determine how many number of electrons that is unpaired by this orbital diagram. So to write the orbital diagram, it's very similar as you write for the electron configuration. Sulfur is S, and you find out the atomic number. So this is sort of the atomic number that equals number of protons, and for a neutral atom, it also equals number of electrons. So therefore, we know we have 16 electrons to find out in the 16 electrons. And for these 16 electrons, where are they? So you can just you probably can start with like write the electron configuration. So that's what we studied like Tuesday. And to get the electron configuration, you first line up those subshells. Line up the subshells from lowest E and then up. You gradually increase those subshells with a little higher energies. And so then this line up is very good for it's true for most of the atoms. There are a few exceptions. So that you just memorize those few exceptions. So for most of the atoms, 1s is lowest. And then 2s will be the second lowest. Then you will have the 2p. And then you will have a 3s. And then you have a 3p. And then 4s, 3d. Right? So today I will show you one very easy way to figure out this sequence. You just use the periodic table counting the atomic number. Right? So once you have this sequence, and you know you have 16 electrons, then you also know the maximum for those different subshells. Right. So we will see the max number of electrons of those different subshells they can hold, and you don't want to like go beyond or exceed the limit, the maximum. So this is 2, 6, 10, and 14. Right? So usually for most of the atoms, you just go by those sequence. Once you get those line up orbitals, you just take them to the maximum. But there are a few exceptions because once you get higher and higher, so those 4s, for most of the atoms, energy is even lower than 3d, but that difference is so small. So some atoms might do a little flip. Alright, so you put a 2 here, put a 2 here, put a 6 here, that's give us 10. You put a 2 here, that gives you 12. So you need like 4 more, you put a 4 here. And so this will be the electron configurations for sulfur. And this configuration, that means you write everything out. So Tuesday we also study condensed notation of electron configuration. Condensed, some people will say this is called a shorthand, but that's very easy. You don't have to write everything for the previous noble gas. So this means the previous noble gas for this one is neon. That means you start from 1s and go all the way to 2p. So completely fulfill all the subshells. So this part in neon. So what you do in this condensed notation, you don't have to write that explicitly. You just write that 1s2, 2s2, 2p6 as the bracket neon. And then you write what level over, 3s2, and 3p4. Alright, so this way and this way, both of these two ways is our electron configuration. Right? And so then the orbital diagram, just as you saw before, just draw the box for each one orbital. Then you know how many orbitals in those different subshells. Orbitals in the S subshell, there's only one. If I adding number of orbitals in those different subshells, in S there's only one orbital. In P there are 3, and here in 5 I have the 7. And you can see like 1 times 2 give you 2, and 3 times 2 give you 6, 5 times 2 gives you 10, 7 times 2 give you 14. But that is the Pauli's exclusion principle, which means for each one orbital, you can only take 2 electrons. And if you have one orbital, you multiply by 2, you get 2. If you have 3 orbitals, multiply that by 2, you get 6. Right. The orbital diagram, again, you have to like usually you draw one box for each one orbital. Right. So now let's do something about the orbital diagram, and for this sulfur atom. So for this 1s, I will draw a box, and for this 2s, I will draw another box. And then for this 2p, I will draw 3 boxes. Right? And for this, so this will be the and 3s, there's only one orbital, so just one box. Next one is 3p, and you draw something like this. So then you just kind of like you have 2 electrons in 1s, and you know this first one is for 1s, and you just put the 2 arrows, make sure the 2 arrows is opposite. And the next one is 2s2, so do the same. Now the 2p is 6. 2p is 6, which means you will have 6 arrows in this 3 box. Okay? The way to like finish this problem is like this. You have 1 arrow, 1 arrow, 1 arrow. Which means if you have 3 electrons, you do them like this. You just spread them out into the 3 boxes and all have the same direction of the arrow. But this problem, we have 6 electrons for this 3p orbitals. Therefore, if you have another one, then before electron called the p4, and this will be the p5, and then you keep adding, so this is p6. Alright, so that's very similar. And 3s2. Now the 3p4. So what you do, you will just 1 arrow, so that becomes 3p2 and 3p3, and you want to have a 3p4, so then the last arrow you can put it in any of these 3 boxes. So right now we have only 3 electrons. The fourth one, and obviously most of you already starting from the first one, you put in the first one. But it's also okay, you can put it in this one or that one, doesn't matter. Alright, so this the so-called orbital diagram, and that is the electron configuration. And orbital diagram, as we talked about before, we have a little more details. So those, they complete the field, and you know that they all have like 2 electrons in each one square. And this is not completely to the maximum, completely fulfilled. Maximum is 6, so right now we only have 4. So then you will figure out the details. You have 2 of these 2 electrons that is not a pair. That is very important. So how many, whether the atom has all the electron pair up or have some electron not paired, is a very important property. Right? So if the atom, all the molecular, all the ion, anything that has some of those electrons that are not paired, and those called so those kind of material, we call them paramagnetic. Paramagnetic. Right. What this means, if you have some material, for example, oxygen gas, example, O2 gas. And O2 gas, even though there are two atoms paired together, but will start like a net structure, use those different bonding theory. So one bonding theory tell you there are two electrons that are not paired. And some other bonding theory will tell you, cannot tell you the picture, but they just say like every, you have this bonding, that means all electrons paired, kind of very, very lame. One theory tell you there's two electrons is not paired. If not paired, that means if you take the oxygen gas and put it into a magnet, like the North Pole, South Pole magnet, it can be stuck in the middle. So even though if you have that two magnets, North Pole and the South Pole, and then you bring the oxygen gas, maybe liquid or something, and because the attraction between O2 molecular and this two magnet pole, so that even can like counteraction with gravity. Well, depends on how big is your drop. Like that, very similar as Millikan's experiment. All right. So that is about the orbital diagram. Right. So again, so the book also do the seminar. You have this few orbital line up, and you find out like in each orbital there are how many electrons. You just put them into like that. Now you do a CRE practice, right? So we have the chlorine atom, and in the ground state. So as we talked about Tuesday. So unless we see something else, we always thinking, assuming we talk about the ground state. Any question about what we mean by the ground state? Because that means the lowest state. Lowest energy state. What do you say? The C. Very good. This will be the, I think will be the 75th. 75. So maybe why you suggest that? Just write your name and 8 on the side. And
So this is the first one we've done, right? No, that's not.
That will be the 75.
No, we should start with 1.
Yes, yes.
Okay.
So they were like easy to read. So once you have the electron configuration, all the orbital diagram, and one very important concept, all the chemists like to have or tell you is the number of valence electrons. Valence electron is the electron that is participate in the chemical bonding and also in some other chemical process and or some of those physical process. It's a very important concept. So we either we will say like either those valence electrons they might not directly participate in the bonding, For example, the CL atom you saw in the last picture, last slide, it has like 7 those valence electrons. And if you take 2 CL atom, here let's use this, use cross. You put them together, they will produce a covalent bond. And obviously, when they covalent, they will share one pair of electrons. That means they will share this one and this one. Looks like all the other 6 is not really participating in the sharing, but they somehow influence this result, even though they are not really in the bonding, but they are also important. That means if you don't have the other few electrons, and you will have a different other bonding patterns. Right. So then we have to see how to find out what atom have how many valence electrons. So to have the answer for this question is you first see like what kind of atom do you have. What I mean by what kind of atom we have is you don't have to worry about you have like those metal and non-metals, because those elements you have different ways to classify them. Right? You see there are some of those elements is metal, some of those non-metal. So then in this concepts, you first want to figure out what are their group number. Group number we talk about in like North America is group A or group B. For example, the last two rows, the so-called those nitinide and actinide. Right. So you have to first identify is your atom is in the so-called group A, and there's 8 of those group A, group 1A, group 2A, and so on, group 8A. So the other type is so-called transition metals. Transition metals, they equals group B. We mainly consider these two groups of electrons. So therefore, you will have a little different rule to calculate or to counting this very important concept. Right? And for this first group, group A, no matter they are group 1A, group 2A, or the group 3A, and you just find out what is the electron configuration. Once you have the electron configuration, you will have those subshells, and like what we did for the last one for the sulfur, right? And for sulfur, you will have 1s2, and 2s2, and 2p6, 3s2, and 3p4. Right. So once you have the electron configuration, and you just identify what kind of element do you have. Is that a group A or group B? So sulfur is group A, group 6A. So therefore, your way of counting is find out what is your highest principal quantum number. So once you have this notation, and you will see what is your highest principal quantum number. Okay. So what is our principal quantum number in these few subshells? Let's identify those so-called principal quantum number first, and we find out which one is higher, which one is lower. Right? So what is our principal quantum number? If I have this, so those are the each one of those one number with one letter is a subshell. Right? Right. So tell me what are those principal quantum numbers? 1, 2, 3. You said bread, right? So this is 1. So now we have this few principal quantum number 1 from this. Everybody agree? And then you have 2 from these 2. And then you have 3 from these 2. Right, so once you get the electron configuration, you know you have all those subshells. Okay? Just identify what are all those principal quantum numbers. And obviously for this set 1, 2, 3. Right. And so now you just see the next is the highest one. The highest one is 3. Right. So then once you have those information, you will see how to count those number of valence electrons, depending on the elements. And if the element is group A, then just counting all those subshells. Subshells in the highest shell. So we already know the highest shell is what? The highest shell, which means it has the highest principal quantum number. So then in this example is 3, right? And how many subshells that is in the highest shell is our third shell. What else that do? So let's underline that. Okay? So the highest, the subshell in the highest shell for this example is our 3s. Okay? The next one is what? 3p. Right? And then from our notation, from our configuration, we know there are 2 electrons in the 3s for this example. And how many electrons in the 3p? 4. So then if your element is group A, you just follow this process, you find out the highest principal quantum number, then you find out the highest shell. And then you know like what subshell in the highest shell. For this example, you have 2 of them. Then the number of so this will be very simple. The number of valence electrons will equals all the electrons in those subshells you find out. So the number of valence electrons for this kind of atom, which means group A, it will equals 2 plus 4. And you know where the 2 come from? Come from this 2. Where the 4 come from? From this 4. So that's how you find out the so-called valence electron, or the number of valence electron for a group A type of atom. It's very simple. Understand? Okay, now do another example. Let's do another example. Let's do the iodine, I. Okay, so what is the atomic number for I? 33. So I will put it here. Just remind you, the lower left corner is the atomic number. Right. So our question is the number of valence electrons. Right. So we need either the orbital diagram or the configuration. Right. Orbital diagram is a little tedious. Okay. Let's do the configuration. Okay. So we were like we're line up those subshells. Line up. sour shells. And this line up is true for most of the atoms. Once you line them up, so then just use electron and fill the sour shell to the maximum. The ion is not the exception, so therefore you don't worry about exception. You just take each sour shell to the maximum. So the line up will be 1s, and 2s, and 2p, 3s, and 3p, then 4s, and 3d, and then 4p. So I need another shell. And then I will start with 5s, and then I will start, you probably already noticed the pattern. So after S, we don't have those lanthanide and actinide, which means the bottom two lines yet. So I will start on the D. And from the last example, you see, if I have 4S, I will start with 3D. So now I have 5S, and what D should I use? Yeah, so you will use 4D. Right, so then after D, you will have, again, you don't have the F yet, so just 5P. I think that will be enough, right? And so now you will just take all those electrons and take this electron to the maximum. Right, so I will put a 2 here, I will put a 2 here, I will put a 6 here, I will put a 2 here, 6, 2. Now how many should I put in the 3D? Very good, so that's 10. And how many will be in the 4P? 6, and then 5S, 2, and then 4D, 10 again. Okay, now you just counting like how many here? This is 10, right? How many here? Another 10, and this is 10, and then you have this is what? 18. Now how many? We have 48 now, right? We need how many? 53. So we need to find more, right?
Yep.
Right. So find more, I just put it here. Alright, so this is one way to get the electron configuration. Okay? Now let's do the so-called condensed. What do you mean by condensed? Just find out the previous normal gas. Put them in, use so I try to change those my background notes into the word. Into the word I can use. You don't like to flip the slide so quick. I can just right. And then just 1S, 2S, 2P, 3S, 3P, 4S, 3D, 4P, 5S, 4D, 5P. Right. So that's exactly the same. And reminding to do this, I line 2, 2, 6, 2, 6, 2, 10, 6, 2, 10, and 5. So we talk about the condense, which means use previous normal gas. Previous normal gas, as you already noticed, is krypton, right? So Kr. So Kr, you are just counting how many electrons in Kr? 36, right? That will be this, 36. Right, so therefore, after that, just write 5s2 and 4d10 and 5d5. Right, so this is two different way of getting the electron configuration. Okay? But for this, for this example, our question is to find out number of valence electrons. But this is very fundamental. So you want to find out the number of valence electron, you have first get the electron configuration of the diagram. Right? So once you have that, so as what we did for solver, you have to see like what kind of atom do we have? Do we have group A or group B? But these two different groups use different rule. Okay, so this iodine, you can, like, I think usually in the periodic table I give it to you on the exam, you will see on the top there is a or B, right? Right. So this is 7A. The very straightforward, very simple problem. If you see like you see those elements in the periodic table, right? So on the top, you write those numbers. If you see the number A or the letter A, you know they are the A groupers. Right. So 7A, and so therefore you use a similar rule. What we say here. So that again, what that means is you want to find out first is what is our highest principal quantum number n. Highest n. Now just use easy notation, which means n is the principal quantum number. Understand? Principal quantum number, that's called n. Right. So now you tell me what is our highest principal quantum number n? 5. There are some other numbers, but those are obviously not the highest, right? You have the first one in 1, and then you have 2 all the way to 3, 4, you count all the way to 5. So therefore 5 is the highest. So once you get the highest, you just identify how many subshells. Okay. So what's the subshell? In this fifth shell. 2. What are that 2? What are the 2? What is the 2 that's in this fifth shell? What are the name for that 2? Is 5 what? 5s? And then what? Very good. What about the 4D? Very straightforward. I mean, that it has a 4, not a 5. Which means not in the fifth shell. Right? And so therefore, you find out that just count like we see we have 2 here, and how many we have in the P? 5. Alright. So now what is the number of valence electrons for this iodine? 7. Okay. So sometimes little confusion if you use this notation. You will see that's normal gas. Then beyond the normal gas, you also have this one in it. But for those A group elements, even though that normal gas looks like those are the so-called the other type of electrons, so-called the core electrons, the normal gas kind of like a core, but that's not really always representing those core electrons. Right? So you have to figure out, follow the procedure. So this is obviously this thing is not counting as these guys. Okay? Alright. So then let's summarize what you obviously sometimes like in the next chapter, in chapter 9, chapter 10, you can use this a lot of time. You want to find out very quickly what is the number of valence electrons for a given atom. You don't have to like every time like use this electron configuration and find out the highest n and find out what is the subshell in it and adding and so on. You can have like a very simple rule. Right? So you can see for this sulfur in group 6A, and how many valence electrons do we have? 6. Right. Now for this iodine, this is in group 7A. How many do we have? 7. Okay. Probably you're going to be people like very can come up with some very bold conclusion, but try that. What is the pattern? Sulfur group 6A has how many electrons? Has how many valence electrons? 6. Iodine group 7A have 7. So what kind of pattern you can see? Maybe as I said, it probably liver like liver growth. You kind of very brave, like it come out kind of jumping out to some conclusions. Yeah. So what's the pattern?
The valence electrons is the same as the group number?
Yeah. So that is a very important conclusion for those A group elements. For A group element, so because both of them is A group element. Get what we're talking about? Right. I can flip it now, right? Right. So now let's finish for the whole picture. For those transition metals, which means group B element, and you pretty much follow the same process. Draw the electron configuration, find out the highest N, and then you also including those like the outermost D electrons. Got that? Probably you need one example or something, right? Let me just get this screen out again. Let's do one example. Okay. Example of transition metal. So give me one example of transition metal. Anyone know the transition metal? Which metal you want to do? Huh? Manganese, very good. Manganese. I think that's not E7, so that's very the kind of manganese. Ma. The number is 25. Right. So what do you do? Okay. Get the electron configuration. 1s, 2s, 2p, 3s, 3p, and then 4s, 3d, 4p. I think that's enough. I will just on purpose write something out, and then you will see. Just I don't want to confuse you. So let's just put the electron in, and so then if you remember the rule, then let's find out the number of valence electrons for this kind of atom. What kind of atom is this? This is for the transition metals, right? Right. So if not E70, once you get the line up, just take each subshell to the maximum. If there is E70, then be careful with E70. So no E70, so therefore you put 2. No E70, you put 2, 6, 2, 6, and 2. Probably I will take a break and see how many we already have and how much are we putting in. How many we already have? 20, very good. So here is 10, here is 10. Right, so 20 now. And you need just put a 5 here. Got that? Right. Very similar process. Find out the highest. So what is our highest N? So now you be careful. I write something out, but you have to find out the highest N, which means what you have to find out the highest N. You use it. Right? So even though some of the N here is higher, but you didn't use it. So what is our highest N?
4.
Very good. So our highest N equals 4. So the rule tells you, you will include all those electrons in something with 4. So what we have with 4? We have 4s. How many electrons in the 4s? 2. Right. So that means you will have 2 electrons for that. If this is your group A element, then that's it. Right? But because this is not a group A element, the sort of transition metals, you also include the right away the inner D subshell. You get the outermost shell. Then the right away there is one that is right inside the outermost. So you have, obviously that's straightforward. If you have 4 is the outermost, is the highest shell, what is the next highest? 3. Okay. So that means you have to also including those 3D. Okay. So for this one, you only have to say 3D. How many in 3D? 5. So that gives you 7. Okay. Then for this kind of transition metals, adding together, right? I see the result. That's so that's I did that on purpose. Right. So so you should get a 5 plus 2 is 7. Now this 7 is the number of the so-called valence electrons, right? So let's see what we did, like a kind of a string for this transition metals is what? Is this guy, right? The inner D subshells. Right. I think that's about it. And let's see the examples. For like GE, germanium. And you do the same, like that. So let's see, we want to find out this guy. So once you get the electron configuration, let's find out what type of atom do we have. That is very important, right? So this, what group is this one? Group A? Group what A? Okay. If you use like what Brad tell you the conclusion, you already know the answer. You already like know one answer for this question, right? So there's 4 valence electrons. Right? So the other answer is how many core electrons, and that's obvious. I didn't talk about that, but then you can figure out very quick. You take the total number minus the valence, whatever way is core. Don't just think about the core is the number of electrons in the noble gas. Okay? You find out how many. First, find out how many valences, then you subtracting. And so let's verify, what Brad said is that the conclusion is right, right? So again, we will find out the highest N. The highest N, usually the highest N you used. Obviously, there's as we talk about like one question from you, like if you have 1 electron, do you only have 1 S? Well, you can have all those subshells, right? But whether you use it or not. Right. So what is our highest N? 4. And then next question is what is subshell in 4? We have 4S and 4P. How many in 4S? How many in 4P? Right. So therefore you have 2 from this, 2 from this. You get 4. Right? Which is right, because we see this for the group A element, the very, very easy way. You just see the group number A, and then that will tell you the number of valence electrons. Now this guy, the core electron, a number of core electron equals total electron minus valence electron. Got that? Okay. Now use this formula. What is our total number of electrons for germanium? You said it's 32? Yeah, 32. So then this formula tells you, you just take the total number of electrons minus valence. How many valence for GE? 4. So therefore you get 28. What do you call this 28 electron? Is our core electron. So again, don't use the number of noble gas electron as the core. Sometimes you might get it right, but that's not always right. Right. I think that's about it. You do a practice. I think this is for the phosphorus. I think use what we talk about, I think very good. You can use like the pattern, me and tell you like you can use first identify for the series P is in like group of 5A. Third one is A group. A group that means A group. Right? For any A group element, the number of valence electron equals the group number. Right? So therefore, only A and B is possible. Right? Why you don't choose? Why you don't choose A? Yeah, so even though the total number electron is right, you cannot have a 3 as 3. Right? The maximum number for S is 2. That's this one, right?
B was the answer, right?
The B is the answer. So now I tell you about this pattern to get the line up of subtails many times. Now you can just use it. That means you have to like remember the periodic table is divided. We divide the periodic table in many different ways. That is metal, that non-metal, that uninoid, that group A, group B. But in this section, you see that the periodic table is divided into the blocks. We have these four common type of subshells, S, P, D, F, and so therefore we will see this periodic table has these 4 blocks. That means which atom or which element in what block depend on the last few electrons in what those kind of subshells. Right? So then the length of each block, the length which means how many. So this means how many columns. Right. So how many columns in each block depend on the maximum number of electrons in each subshell. Right. So what is the maximum number of electrons in S subshell? 2. What is the maximum number of electrons in P subshell? Okay, so that tells us the S block should have 2 columns, and the P block should have 6 columns, and similarly the D block should have how many? 10 columns, and the F block should have like 14 columns. Right. So that is my paragraph. Right. So then the principal quantum number of the S and the P orbital that fill across the rule equals to the period number. Right. So you are counting. So to use this method, you are just counting the number of electrons until you get the number of electrons you want. For the last few examples, or so far you want to get 16, you're counting from 1. Right? And you counting those atomic numbers. Right? And then you are, once you counting like 1, they will say 1 is the first one in what block. Right? Then counting 2, they say 2 is in what block. And so then you will see, if in that block you will use either, if in the S block you will use S. If in the P block you will use P. Right? So then you will see you use what S or use what P. So that will depend on when you counting, if you counting that atom or you count that number, and you see you are counting right now in that second period. If in the second period, if you add up or you adding as like something P, you use 2P. Right? If you adding somewhere with S, you use 2S. So this is what this paragraph tells you. So then once you get that electron configuration, you already know this result, the period, this result, the group number equals, for the A element, equals valence that's kind of also your results. Right. So I will get the period table, then we'll see how we counting that. Right? And I depend on you, like you already memorized that a few rules. So let's pick up one element, and we want to find out the electron configuration, and we will just counting that. Okay? So let's see, we will find out the electron configuration, for example, for this nickel, for this Ni, right? And you know, Ni has like 80 electrons. So I said just starting counting, you need to counting like one by one, and here you get 28. And this period table is very clearly tell you what block is what block. So in the middle is P block, here is P block, except that one is also S block, and here is few F block. Right. So the rule is you counting that. If you counting those S and P, what S and what P, just use the period number. If you counting you ending up somewhere like in the D, just use the period minus 1 number. Right. So that's counting like starting with 1. 1 is here, right? And then this will be 1 as 1. Right? How do you know you're going to use 1 as 1? Well, this two information. You know you have to use 1 because that is period 1, the first period. So this is so here, those numbers are what? Period number. Okay? And so therefore the H, the first one, the number 1, the atomic number 1, atomic number 2, atomic number 5, just counting the atomic number. And here you get the number that matching your number. Your number is 28. So obviously 1 is the first one you start. Right. So atomic number 1 is 1, that is in the so-called S block. So therefore it is S. As 1 comes from that in the first period. Get that? So the number for the S and the P is the same as the period. Right? Now this one has, this will be our number 2. Right? The helium is number 2. Now helium is in what block? Just by the coloring S block. Now then you have to see what S. The helium is in what period?
1s.
1, so 1s. How many electrons we have?
2.
So therefore 1 is 2. You adding 1, you adding like adding minus 1 and adding 1 minus 2. Right. So then you keep counting, you have 28. So that's number 3. Where is number 3? This is number 3, right? Number 3 is Li. Now Li is in what block? S block, so therefore it's S. So right now I think you get the picture, so I'm going to erase all of those. I just write here, minus 1 and minus 2. And lithium will be, you still have all of those because you had counting to 3. You still have that minus 1. I mean, you still have that minus 2. You don't have to use minus 1. Use the previous result, right? But you keep those in mind. So this Li should be what? In what block? First is in S block, right? And what period, so what S shall we use for lithium? 2. Okay, 2 as what? That's 1. So why 2 as 1? Because Li altogether has 3, so you already have 2 here, then you get that. So you're adding 1. Right, so the next one is B, beryllium. Beryllium is also in what block? S block. What S again? 2. Why 2? The second period, so therefore you're adding 1. Alright, so that was the liberal confusion. I said, I think at one time I said use the previous, but not use all the previous. Okay? I mean, once you get one for each like 1 atom, you want to get the final result for your, of electron configuration for your atom. You use some of those previous. Obviously, you don't want to write 1s1, 1s2, 2s1, 2s2 for your beryllium. Right? So for right now, if you want to write what is the electron configuration for beryllium, you don't write 1s1, and 1s2, and 2s1, and 2s2. So that's not right, right? So what you write for beryllium for this Be, just 1s2, and then what? 2s2. So that's still, you still use some of those information, like how you like counting that, right? So we were like keep going, and I think we don't have time to go over all those elements. So we said we want to do like that for nickel, right? For nickel. So I was jumping over that to this kerosene. So if the last electron for this Ca will be in what kind of subshell? What subshell? In S. And what S? Will be 4s. Excellent. And 4s how much? 4s 2. Very good. Very good. Now if you keep going, and you will see the first element here is a scandium Sc. And from this color, that means it is already in what block? Okay. Let's just write one, like starting from Sc, and we're going to use D because it's in D block. Okay. So that's kind of straightforward. Then we have to figure out in what D. In what D should we use? Andrew, what D should we use? The 5?
Yeah, sorry, 3.
3. So the number for the D is this. How do you find out 3? How do you get the 3?
It's just a pattern. So instead of being in the third row, the whole D block is dropped down. Or, I'm sorry, P block is dropped down. No, what is the D block? D block is dropped down 1. So instead of being 3 at the actual 3 row,
It's hard to explain.
yeah,
It's just one less.
right. It's 1 less than the.
Just one less than the period number, right?
Yeah.
Okay. So the period right now for the Sc is on the fourth period, so therefore just one less. Right? So now this will be the few last electron that for this scandium, obviously you have to keep going. Right? So then the last few electrons, you will still have the 4s2 for this nickel, right? And then this nickel is in this block is in the D block, also in the D block, right? So as we asked the Andrew, so this will be also the 3D. Now 3D what? Yeah, if you notice everything, just adding like those, 8. All right. So then, this is the last few electrons. If you want to summarize, you can summarize what I did for the beryllium, but you can also use one notation called the condensed. I think that one is ready for the condensed, right? So if you want to use the condensed notation, we can just think about this one. Right now we have this 4s2 3d8. And what do we mean by the condensed? How we finish the program with the condensed?
Just put R down and put it in brackets.
Okay, because what Don, this R here,
Yeah, because it's the last complete double gas.
the previous normal gas, so just write R down, and then the angle bracket, and that's probably this one, 18, and then once you finish the 18, you add in this one, you get 20, you get this one, you get 28. Alright. So that is one example of using the periodic table and the blocks. Right. So that's similar here, and we'll see that. I think that -7 here is also S, and those are the P and D, and then this two bottom line of the F. Okay, so here is one example again. If you want to get the electron configuration for the phosphorus, so you are just did what we said on the last example. So you start with usually start with a pre-normal gas. that's 3D2, and 3S2, and then 3D3. Alright, and so let's do another practice. I think we already repeating that, and this example is for the selenium SE. Right? Alright, so what do you think? Let's do like one by one. That kind of review. Okay? What's probably the configuration for this H1? That will be 1S1. And what's the configuration for this? This color is not even right, so this. But anyhow, this S block, B block, this is the S block. Alright, so this probably this helium is what? So our 1S2. Alright, so I will just randomly jump up with a few. Now let me see what will be the configuration for magnesium. What will be the last electron? Not the configuration, let's just find out the last electron for Mg. That will get into what? Last electron for this Mg, probably the 3s, the second one, 3s2. Very good. So then that's similar. Let's find out this. For the zinc, what will be the last electron for the zinc? Okay, so it means you will see that because in the phosphorus so the 4s something, right? So 4s2. And then those area is the D block, right? And D, so I think that's what Andrew just said, right? And this will be the 3D. And here you are having enough electron put all to the maximum, so this is 10. Right? Very good. So then let's do a few here. Let's find out the last electron that for this GE. You see my passage? It's the last electron for those elements. Okay? What will be the last electron that in for the GE? In what block? GE in what block? P block. The P and S, what is the number for P and S? It's the same as what? The S number and the P number is the same as what number? The pair number. Right? So this is the fourth period, so therefore it's 4P. But, and just counting, see, this is the second column in the P block. So that will be this will be the 2. Right? Good. So once you get that, and this the last this was our pattern, and this will be our is also in the P blocks, and again it will be P block number. P number should be same as the pair number, so it's 4. So that's about that, right? Now you put them together. You just use the previous completely filled subshell. Don't use those half filled or something. And or you can use the previous normal gas. So I think that's simple enough. So what you get, use the previous normal gas is argon, because that's the previous. And then you have that 4s2 for that block, and 3d10 for that block, and 4p4. Alright, so I think you once you have this, and you can also like do a practice, find out what is the number of valence electrons. If you use like what so we find out the pattern, you don't have to even use the configuration. Yeah, in the column, this is the group of what? Those 8 group elements. If you 6A, that means it's 6. Now, if you don't use this pattern, use what we write here, that means you have to find out that what is our highest principal quantum number n from this configuration, what is our highest principal quantum number n?
4.
4. There's argon here, but argon, I think that is in the third period, right? So no, you can get a 4. So therefore, the highest one is 4, right? So then we have 4s is one Sauer and 4p is another Sauer. Get that? So 2 Sauer in the highest shell. All the electron, like for those group A elements, in the highest Sauer is our valence electron. Get that? So we have 2 here, and we have 4 here, and any together get 6. That's why I get a 6. Right. So then, don't forget there is another concept called the core electron. Core electron equals how many for this example? Selenium is what is the total number? Core electron we talked about before, the total number of electron minus valence electron, right? So what is the total number of what do you say the selenium?
34.
34. That's 34. And this one you have a 6, so therefore 28. Right. Any questions? Yeah, those very simple questions. So do a practice so you can decide the configuration for the net. We still don't have those exceptions yet, so therefore you just line up with the periodic table as help. Where's the net? So then we circle net here, right? Adding 2. I don't think it's A. C. Let me say. C. Why not D?
Because it has 5
Why not D? I think that's also the total number for you, right?
Because it has 40.
You have 40. You cannot have 40. The D is how many less than the period. So this is what period? This is 6 period, right? So D should be 1 less, and that's the problem. If you have that 6s, and this should be the 5, so therefore it is C. Then you compare C with B, so why not B?
Also use the wrong number gas.
Why not B? Because this normal gas is not right. So the previous normal gas, and the previous normal gas for this guy is this. Right? I think you find out. So that's how you study. So make sure you study all those choices. So it's C. Right. So then we talk about the transition metals. Transition metal is in the D blocks. So that means the last few electrons that were you put in will be in those D subshells. Okay? Remember those D subshells is like 1 less than the number is 1 less than the period. Okay? And so now we begin to talk about those exceptions. So sometimes, so those, for example, the 4s is is lower than the D, but some of those atoms, they are going to like do a little like some strange things. That means they will promote those electrons from the S into the D. So zinc is not exceptions. So you find out that zinc, what we did before, is the last element in that the first D block. So therefore you have the 3D10 and 4s2. So you will see the exception. I think the exception is the chromium. Okay? See the chromium. This is the result. You get this kind of configuration of diagram. from some of those experimental results. Got that? So what is strange to you? What is strange by looking at this configuration of the diagram for this CR, or this chromium? What is strange you think? You get right. So S, and see here is 1, right? And according to our usual line up, the S, like the 4S, is a little lower in terms of energy than those D. But we talked about it many times before, so the 4S and 3D energy difference is so small, so therefore some of those atoms really not follow the similar pattern, and they just flip. Got that? So that's probably not really that difficult. Okay? And then another block we did not talk about in detail is so-called F block metals. That's probably never confusing. So very similar as the other block. If we call that is F block, that means the last few electron is in the F subshells. Obviously, for every block there are some of those. Not for every block, for most of the blocks there are some of those exceptions. And what are the exceptions for the F block is sometimes you're going to use those D orbitals, and before like really you should like use the F, and you should like finish all the D, but sometimes you will not finish all the D, and you already can use F. But those kind of exceptions, right? So usually you just know like a few very important exceptions, and all the other exceptions you should like go through that, run through those blocks. Once those elements go through those blocks, that means all those blocks will be completely filled. Right. So this, for example, this uranium. So in the F block, so we call that EU number 63, right? So right here, European, and so that one is not the exceptions. Okay? So what you see is you will have this 6s2, and you can see the location from the periodic table. So this one is the uranium here, and somewhere like a squeeze between here, and it uses S, and then out of S. And if for the other period, for those period that is number 4, number 5, out of those S, for example, these two rows, it will like getting on those D orbitals right away. But these last two lines, in the so-called F block, so therefore out of those S. They did not use those D yet. Other some of those exceptions, I think for these two guys, for this lanthanum and the 89 and AC, we use one of those D orbitals before they use the F. So as I said, you don't have to memorize some of those exceptions. And so here another like example of those F block, and you can see that exception clearly. And it's supposed to use those F first and those D, but those energy is so close, so therefore they sometimes use some of those kind of patterns. I think for us, the important exceptions is about that 4S and 3D. So that is the important exception. There are many other exceptions, but not that important to us. And those exceptions is the result of experiment. You don't have to spend like many times to memorize those experimental results. So the expected behaviors for these few elements is you can see very similar. They all have those S, maybe 4S, 5S, 5S, and take it to the maximum 2. And that is the so-called expected. So that's for most of the atoms, that is the pattern. But the exception, that means they either like take one electron away from that 2 and put it here, and or take all the electron away from that and put it into the D. And those are the exceptions. And why we want to like see those exceptions, not because they are simple to memorize, because we have some of those reason to give a better understanding. The reason to better understand those exceptions is that you can see after they change, after they have those S2 become S2 and D4 become S1 and D5. So that's give you the pattern. So this D1, I mean the D5, S1, both of these two subshells is half fill. Okay? And so half fill compared with those like nothing, so this 3D4 is kind of nothing. It's not half fill, not a completely fill. Is stable from those models, from those calculations. So sometimes that makes sense if we accept those calculations. But we did not do calculations, so sometimes some people like kind of difficult to see how you show me that makes sense. Unless you really like you personally doing all those tuning or modeling, see the result. Right. So that is the exceptions. So now from those, what we want to learn is from those configurations, not really from those exceptions. Once we get the configuration, and we can understand those property of the atom or the periodic table pattern from those configurations. So before we started this Chapter-8 and Chapter-7, we know some of those periodic pattern for the elements. For example, elements in the same column have similar properties, like the group 1A, lithium, sodium, potassium, all are very active metals. And group 7A, fluorine, chlorine, bromine, iodine, all like very active nonmetals. Group 8A, helium, neon, argon, krypton are all not very active, neither we call them nonmetal, but they're just not very active. So those are the patterns we saw before these two chapters. Now this chapter will help us to understand why we have those kind of patterns. And there are some other patterns, elements in a period. You know what is a period, right? A period are those rows that go from left to the right, have a repeating pattern. So that's difficult to understand. What is a repeating pattern? For example, repeating pattern we talk about is let's say those group period second period and third period. So both second period, third period, you start on the left side in the metal, then go to the right side non-metal. So that's a pattern. And then you go to the third period, have a similar pattern. And with this chapter, you can also understand that. So the bottom line is those pattern, okay? Those pattern we saw here is because those electron configuration have those kind of patterns. So they either have the similar electron configuration or the electron configuration repeating the previous period. Right, let's see the examples. Example is group 8A. You already talked about group 8A is very not active. And the reason for that is you do the calculation, you will see that they have those sort of the completely filled outermost shell. So then, according to the model, the energy you get will be lower. So even though they will have a different number of electrons in the outermost. So here for helium is 2. So this is the outermost shell. So even though they have a different number of electrons in the outermost shell, for helium is 2, for all the other is 8. But the similarity is they have a so-called completely filled, not half filled. Right? For those outermost shells, they just completely filled. And according to our model, if you put electron in those kind of orbitals to the calculation, and then you compare with UT electron weight, you still have the same number of protons, and you will see the energy you get. Remember that the equation give you the energy, give you the quantum number, give you the psi, and then compare that, you will see the energy is lower for that. So even though you have one more electron. And so that gives us some idea. So that means some other groups should have a similar pattern. Right? So all those groups are in group 8A, they are completely filled, so therefore they are all stable. And if you see the other group, for example, group 1A, right? They are all active. So why they are all active? You see their electron configuration is something S1, and how many S1 depend on the period. So lithium in the second period, so 2S1. And sodium in the third period, so 3S1. But again, the pattern is, so they all have like one electron in the S subshell. So that tells you they have the similar property. And they have a similar configuration. All of them has S1. And those halogens in group 7A, and they also have similar chemical properties, so they are all very active nonmetals. Why is that? Because they have similar configurations. S2P5, S2P5. So all of those have like 7 electrons. Now let's go back to talk about how they become, in what way they become like active. They become active in the chemistry. That means they either want to gain more electrons or they want to give out electrons. Right? So pretty much they want to be stable. Now we already found out in the last slide, the stable configuration is noble gas. Right? So therefore, most of the atoms, and they want to be stable as noble gas, even though not really everyone can get the final result as noble gas, but they want to get somehow getting closer to noble gas. Right? So noble gas configuration is a completely filled outer shell, either 2 or 8. Right? So then let's see, those other atoms, how can they get something like those noble gas? Right? So let's see, one group is group 1A. Group 1A has one electron, one more electron than the previous noble gas. So helium is number 3. The previous noble gas for helium is neon. Right? So what that means is if lithium wants to be stable, become stable, right? if lithium wants to become stable after a chemical reaction, it has two ways to go. Either to be like helium, that is the previous noble gas, or to be like neon, which is the next noble gas. The easiest way for lithium to be stable is because lithium is closer to helium. So therefore, it's a little easier for helium to lose one electron and become very similar as the helium. Right, so that's tell us a couple of things, and tell us first of all, lithium wants to be stable by lost electron, and then lost how many? We say lost one electron. Because after you lost one electron, you get two electrons that is same as helium. And that is what we study in chapter 1, chapter 2. We see lithium like produce 1 plus, and not 2 plus. Right? And then opposite, you will see those non-metals. Non-metal is on the other side, on the right side of the table, they closer to like the next noble gas. For example, the fluorine is number 9. And the next noble gas is neon, number 10. The previous noble gas for fluorine is helium, which is number 2. And again, you have two ways for this fluorine to be stable in a chemical reaction. Either like lost all those 7 extra electrons. If you take 7 away from the 9, you get 2 that become helium. Or you want to receive 1 electron that become 10, as similar as neon. And it's really easier for this fluorine to just receive 1 extra rather than lost all the 7 to become similar as helium. So therefore, all those group 7A elements, they just much easier to become stable by receiving 1 extra electron. Obviously, if you receive 1 extra electron, you become 1 negative, and not 2 negative. If you receive 2 electrons, that means not like the noble gas. Right? So that's really like show us some of those reasons for what we have been studying since like the beginning of this class. Get that? So this is kind of the fundamental like the number we want to use, so-called 8, 1, 8. So this 8 and 1 electron is kind of our rule of thumb. The rule of thumb, that means not precise, kind of like a ballpark number. And you can use 8 as a rough guideline. So some elements, 8 is stable. You see the noble gas, like for neon and argon, krypton, they are stable, have 8. Atom stable not depend on not only the noble gas, obviously it also depends on how many protons in the nucleus. Right. So then, a very important concept in this chapter is about those pattern for the size of the atoms or the ions. And so then, what is the size is about those atomic radius. You can imagine an atom is like a spherical ball, right? And so then you have this radius r. So for the radius r, the pattern is pretty good, and you just go like the pattern. Whenever we talk about pattern, you think about 2 patterns. So you go like up and down, like going like from bottom to the up in the same column, or you going from left to the right in the same period. In the same period. And also remember, when we talk about the same period, we usually will skip those guys in the middle, because they have their own patterns. So just think about those group A, and from group 1A to group 8A. Right. So for this atomic size, the pattern like this. Okay. One pattern you will accept totally. The other pattern you can say, wow, what can that happen? One pattern is you going from, for example, in the same column, from the top to bottom, increase its radius. And if you pick up one row, let's see this second row, start from lithium, beryllium, then to neon, you can see the number is getting smaller and smaller. There may be a few exceptions. I think not too many exceptions. You don't have to really worry about that. So the number you use them carefully. Maybe one of them just not what we said, but those not important. They just kind of random errors, right? I said one pattern you will understand. You're going from top to bottom. That become bigger. You will accept that because going from bottom top to bottom, so the neon has like 10 electrons, and then you go to like pre-veterinary has like 54. Or xenon has 54, obviously you have more electron, and your atom getting a lot of radius, so then you think that seems to make sense, right? The other pattern totally like, see what can that happen is like the second one, lithium has 3 electrons, and the neon has 10 electrons. You add more electron, your neon getting like smaller than lithium. How can that happen? To understand that, you have to use the quantum mechanics model. We talk about we have those electrons into those shell, solid shells, right? So to talk about this, one concept that we learned before is about the shielding. You still remember the shielding and the penetration? So in a multiple electron system, electrons are simultaneously attracted to the nuclear. Simultaneously, that means you are attracted and you also repelled by something else. Right? Because you have electron kind of repels. It's very interesting that how much repel the electron or a field or experience depends on where the electron. The electron in what do we mean by electron? Where the electron? You mean the electron in the S subshell or in the P subshell? So all the electrons are shielded by the inner electron. And so then those outer electrons, you can also think about those outer electrons, they also shielding each other. They will also like kind of repel because they all have negative. But their shielding is much less because they are on the same level, in the same distance. Right? So because the shielding, so those outer electrons will not have that, will not experience, and will not feel the full strength of the nuclear charge. So we know that before. That's the reason we have that 4s, energy is lower than the 3D. If without the shielding penetration, everything 4 should be higher than everything 3. But because of shielding penetration, so that 4, even though the higher level, you're more outside, and have a little chance of getting inside. Once you get inside, get more attraction. And because of that, the energy is a little lower. So now, what is really the net? So this, we have a different name. It's very similar as this word net. You have all the positive charge in the nuclear, and then you have the electron repair, so that will take some away. So then you have the net. So that's called the effective. So the effective nuclear charge is the one that will help you or make you understand why lithium even has less electron, is bigger than the neon, even though that has more electron. And there's a lot of effort to try to calculate more precisely what is this number, the so-called Z effective, from those atomic number, like how many protons inside the nuclear, and how many like electrons that can effectively screening or shielding that electron by using those kind of formulas. So you will find out the effective nuclear charge equals the total nuclear charge, and then subtracting by some numbers. Right. So then, when you find out, you will find this pattern. This pattern is referring to the magnitude or the number of this. Is totally opposite as what we talked about in the first few sections is about the energy of these two subshells. So we talk about this energy of the few subshells. In the same shell, the S subshell is lower than P, and P is lower than D, D is lower than F. Why is that? That is because this number, okay, for the S is larger than this number for the P, which means those electrons in the same, in the S, maybe 4S, is stronger, even stronger attracted to the nuclear compared with those electrons in those 4P. Got that? So that's your sort of so that we go. Those are sort of the screening and the penetration. Okay? So again, the example is lithium. Lithium has 3 protons inside, 3 electrons outside. But you have to have those details. So what are the 3 electrons? Where are they? If you write the electron configuration, you will see 2 of that is 1s. The other one is 2s. What is the difference between 1s and 2s? Is the radius, the size. 2s is bigger, so therefore 2s is even more outside. And when you spending most of the time outside like that, and this blue area really can block your attraction to the proton. All right, and so you will see these results for the atomic size. Now this picture, you understand this picture by what we talk about the 2 pattern. The 2 pattern is in the same group and in the same period. What do we see in the same group? In the same group, let's say that group 8, group 8A. So group 8A, and let's say going from top to bottom, what happened to the size? You remember the pattern? What happened in the same group going from top to bottom? The radius getting smaller, getting larger. Larger. So you see here, so helium, right? And so these are the group 8A. Okay? You see the number? Getting like from somewhere like 70 something, right? And gradually increases, but 125. And that's a group pattern. And now period pattern. Period pattern. And so let's see, this is our second period, this is our third period. And this is our fourth period, and this is our fifth period. So again, when we talk about the patterns, you have to skip those middle guys. So these few middle guys, that's for the transition metals. They will have their own patterns. But so that those patterns are pretty good. You can see there are maybe few details going like up and down a little bit. So what do we set the pattern in the same period? Let's say going from for the second period. So this is the left side, and this is our right side. What's this picture tell you? In the same period, in the second period, going from left to the right, what happened to the radii? Decrease is getting smaller, right? Yeah. Why that? That is because that number, Z effective, so this is Z effective. What is Z effective again? Very good, the net nuclear charge, the electron field, electron experience. So one very approximate formula for the calculation is just atomic number, Z. Whatever the number for your atom, just take the atomic number, okay? Minus what? Minus S. S is like the sort of the shield. How many electrons that is shielding your electron you want to consider. Well, you find this number is easy. Just use the atomic number. Okay? Use the atomic number. For example, you want to find out the number, the atomic number for lithium is lithium 3. And then, now this number, you want to get a precise, not that easy. Okay? So one like the very very rough first approximation is use those core electrons. So if you do the calculation, use this one, use this simple approximation, and you will find the pattern. You will find the pattern. Seems you are interested in finding out the pattern, right? So let's see our second period. We have that Li, and then we have that Be. The second period we have nothing in the middle. Then we have boron, carbon, nitrogen, oxygen, fluorine, and neon. Got that? And what are their atomic numbers Z? And what are their Z effective? Maybe I should just abbreviation. Alright, and you see what are the atomic number for lithium? Okay, right? So the atomic number for lithium, this is 4, and 5, right? 6, 7, 8, 9, 10. Now use our very like this rough approximation to take that Z effective equals Z minus S. And see what we say Z is the atomic number. The very first approximation is what is the core, what is S? S is the core. Well, the core for this period, that means the previous number gas. So all of them has the same core, same S. Right? So for this second period, S equals 2. Even though this is really a rough approximation. S is 2. Why S is 2? Because then the core electron. You can figure out the core electron for all these 8 elements very quickly by writing the electron configuration and then find out the highest principal quantum number. You get that? Well, let's see the S. S equals, for this approximation, is our core electron. What is our core electron when we started? So when we started before, core electron equals what? Total electron minus what? Valence electron. Right? So total electron for this lithium is what? 3. How many, what is the valence electron for lithium? 2. So lithium group 1. Group 1, I mean, you saw can get 2. But lithium group 1A, group 2A. Right? So I think what you said, you've heard it. All of them has 2. So all of them has this number 2 for their S. 2 and 2 and 2 and 2 and 2. So this is approximately, maybe not a good number, but you know that's. Now you do the very simple calculation. You take the Z. So this is not 2, this is Z, right? Z minus S. For lithium that become 1. For this will become what? 2, and then becomes 3, 4, 5, 6, 7, 8. What is important, I said before, is this number, the pattern for this number. Okay? See the pattern for this number? Okay? Going from left to right, this number increases. This number increases doesn't mean your atom getting bigger. You have to think opposite. Right? So if this number increases, that means you have more attraction. The nuclear has more attraction to the electron. What happens?
Smaller.
Yeah, means smaller means shrink. So that is kind of like, if you don't study this chapter 7, you don't have those like cross electron and those shell idea. It's difficult to understand why you're going from left to the right. You're adding more electron, but the atom of the ion will see later, and you're getting like it's getting smaller. So that's what we talk about. The larger the effective nuclear charge and electron interference, the stronger the attraction it will have for the nucleus. Do you agree? Right? Because that is sort of the net. If you have some of those blocking, more blocking, then means you have less attraction. And then you use your like very simple like rule. The stronger the attraction, the valence electron have for the nuclear. What is the valence? Valence pretty much those outermost electron, right? And the closer they are, every distance will be to the nucleus. So then that means conversion across the period increase the effective nuclear charge as we show here in this very simple calculation. So this pattern here is these few numbers, right? So those few numbers increasing pattern. I said this chapter is kind of easy, but you have to see increasing what and decreasing what. So this the attraction is getting increases. If the attraction is getting increases, and that makes the atom getting smaller. The other pattern is very easy to understand. Okay? The other pattern is using the same column and going from top to bottom. And why is that? That is because the size of the atom is related to the distance the valence electron are from the nucleus is very same as the period. The larger the orbiter, the larger the atom. Why the larger the orbiter? You adding like remember what we did for the configuration. So whenever you like increase the period, you increase the number for the S and P, also the D, right? So that means you are adding a shell. Okay? It's kind of like the winter time. So every week you adding more and more layers. So this week you adding like a jacket, next week you adding like a winter coat. Right? So that is the reason for the same, in the same column you're getting like a block and block. Okay, now the transition metals, they don't have very good group, very don't have good patterns. So one pattern you will see like also compare like in the same column. So I changed that this like a little bit because you will see that I think in this chapter, so you will see something like in chapter 24 you will see something else. But you can summarize just like that. So I think in the for the transition metals, you're going from transition metal, I did view like a block here. So this is the first group of transition metal, the second group of transition metal, and then the third group. Okay? So in the same column, we also have the same column, and from top to bottom, increases but not always. You will see this one is bigger than that, and this one bigger than that. That also makes common sense because there's more electron, more shell, more layers. But then suddenly if you compare like this with that, 3 with 2, 3 with 2, it's kind of like not a good pattern. Sometimes bigger, sometimes smaller. Pretty much they are the same. Why is that? Because you have the so-called lancing night contraction. And why lancing night contraction? You compare this number 3 transition, number 3 rows, like the osmium with ruthenium. The difference between these two atoms is 32 electron difference. So there are 32 more than that. 44, 76. Now that is quite interesting to study those chapter 7. So then it depends on where you put the electron. So you know there are 32 more electrons, but 14 of that. When you go from that, when you compare this Ru to S, 14 of that 32 You're going through this, is it here, 99, going through those F block. And F block is those F orbital, remember those F orbital kind of like spread out and has like 8 loops. And so they are not very good in like screening. So these do not blocking very good. Right, so that is about the transient methods. And the other pattern is like you moving from left to right. Not many change, so they pretty much the same. And if you compare those group of 1A, group of 2A, group of 3A, left to right is relatively smaller. Why those transient methods not getting smaller? It also have the reason, because when you put in those electrons in those are sort of N minus 1D. N minus 1D, even though the energy is higher, but physically they are outside, and they are inside. Physically, so this one is outside, so therefore, you put them inside, you will not change your size too much. All right, I think that we will like start here and we'll to the left.
Two lab, right?
Yeah, 2 lab, pretty much just like 1 lab, like 2 part A and part B.
Part A, part B.